Hello students, my name is Shashank Shekhar and today is the fifth lecture of the chapter Aldehyde Ketone and Carboxylic acid. So today we will see the reactions of your aldehyde and ketone. We have seen this Clemmensen and Wolff-Kirshner reaction. Today we will see the mechanism of those two. After that we will see some more topics. So that topic would be this, that is aldol reaction, acid catalyzed aldol reaction. So it can be done in two ways, using acid catalyzed and using base catalyzed. Then we will see illustration of this aldol reaction. So there are types of aldol reaction that can be possible. We will see to that. After that, we will move to Cannizzaro reactions and see its mechanism also. Now all these reactions that you are seeing here, that is dependent upon the availability of this alpha hydrogen. So what is alpha hydrogen? We will see it. But for now, let us see the mechanism of Clemmensen reduction first of all. So this is our ketone. So what happens in Clemmensen reduction? For Clemmensen reduction, basically in Clemmensen reduction, we take zinc amalgam and we treat it with zinc amalgam, our aldehyde or ketone, and our aldehyde or ketone is reduced to normal alkane. So what is the first step here? The first step is protonation. So you can see that the oxygen of this carbonyl group is taking this H plus and it is being protonated. Now what happens due to this protonation? Guess it. Okay. So it will now bear positive charge. Since it is bearing positive charge, this will increase the nucleophilicity of this center. Okay. This will increase the nucleophilicity of this center. Why? Now, because this is due to the presence of this positive charge, that its electronegativity of this oxygen has been increased and it will attract more and more electron density towards itself. Now this will reduce electron density of carbon and hence increase the nucleophilicity of the center. Now what will happen in the next step? Zn will donate electron. So electron donation will take place. So what is Zn here? So Zn is basically zinc. And what is zinc? Zinc is a metal and it can donate electrons. You must have studied this primitive definition of your metal, that metals can donate electrons. So here this zinc is a metal, so it will donate electrons. Now as it will donate electrons, this pi bond that it is between carbon and oxygen, it will move on to oxygen and neutralize the positive charge on oxygen, therefore making this kind of chelated compound. Why I am saying it is chelated? Because in this case this carbon center is being chelated to this positively charged zinc. And also now and also this and what is the difference between chelation and your normal bond? So you can see that this is not a normal bond, this is a chelation. And why is it so? Because this is basically due to the interaction between the carbon and zinc and not due to the actual bond formation. After that, there is also Cl minus in your mixture. What does Cl minus does? So Cl minus basically forms bond with zinc to make this, or you can say to neutralize this positive charge. Now again this zinc, another zinc will take this Cl and we will have Zn minus. So you can see here. So before that this oxygen that is present here is being protonated and it is thrown out, or you can say it has left this group, forming H2O. And you know water is a very good living group, so it will leave this center and create a positive center here, that is a carbocation. Further, since it is a positive charge, so to neutralize it, this zinc will donate electrons and also this Cl will be taken up by the second zinc atom. Here you can see it, that this zinc is taking the Cl atom, Cl atom, and the negative charge that is being accumulated on zinc is further transferred to this positive charge to neutralize it. Okay. Yeah. Further, this zinc, this kind of interaction is formed because this zinc has now donated 2 electrons. Now this has created a negative charge here and a positive charge on zinc. So basically what is happening here? So you can see that zinc has a negative charge here. So this must be due to an extra electron, and there is a positive charge on carbon. And what is the reason behind it? It is due to a less electron. Now what happens? This zinc has 2 electrons. It donates both of its electrons to the center. So first one electron will neutralize this positive charge and the other electron will create a negative charge in center. Similarly, one negative charge donation will neutralize this negative charge, and another electron donation will create a positive charge on this zinc. Now we have a negative charge here, and we are doing this reaction in the presence of HCl. So if you remember the reaction, it is ZnHg and HCl. So this H plus that is present in the solution is taken up by the negative charge. And after this, what will happen? This Cl minus will again take this zinc and will again create negative charge on the center. This same process will be repeated here. If you look here, so this is the process that is being repeated twice. Okay, so the same process repeated here, only the sigma bond between these two atoms are now transferred onto the carbon center rather than your zinc center. Clear? So this will create again a negative charge, but since the solution is acidic, it will again be protonated. So at last, this chelated zinc will be removed and it will be protonated to form this alkane. Now in the overall reaction, what happens? Our carbonyl group, that is aldehyde or ketone, is produced in the presence of ZnHg, that is zinc amalgam, and HCl. Now why is this zinc amalgam used? So this zinc amalgam is used in the reduction as the reaction of the zinc with hydrochloric acid. So zinc react with hydrochloric acid to produce H2 gas. So it is used. Clear? So this was the mechanism of Clemmensen reduction. Now we will move to Wolff-Kishner reduction. So if you remember what is Wolff-Kishner reaction, so in this reaction basically what happens is we take a carbonyl, that is aldehyde or ketone, we treat it with hydrazine, that is NH2NH2. This is called as hydrazine, and this NH2NH2 reduces this carbonyl center to your alkane. Now how does this goes? So this is the reaction of aldehyde and ketone with hydrazine. This produces a hydrazone, and this hydrazone is further hydrolyzed in the presence of a base. So reaction of a base with reaction with a base and heat converts the hydrogen into alkane. Now let us see the mechanism. So what happens in this mechanism? We have a carbonyl center here and we have a hydrazone. Now the structure of hydrazone is such that it has a nitrogen and it is bonded to another nitrogen, and both of these nitrogen are instead bonded to two hydrogens. Now you know that after completing the valency of this nitrogen, there are electrons still left on this nitrogen, and electrons are nucleophilic in nature. They are attracted toward the positive charge, and you know very well, we have seen the structure of carbonyl, that there is a nucleophilic center in a carbonyl. So this electron that is present on nitrogen is being donated onto this center, creating this kind of intermediate. Now as these electrons will be transferred onto the center, the double bond between carbon and oxygen is broken, and one of the pi bond is transferred onto oxygen as a pi electrons, and one bond is formed between the nitrogen and your carbon. Now since nitrogen has donated one electron, it will also acquire a positive charge. Further, the interproton transfer will take place. You must have heard this term IPT. What is this? Interproton transfer. This was used during the reaction of sodium bisulfite with your carbonyl center. So here also we have seen this. We will see the same phenomena occurring, that this H plus that is being present on your nitrogen, that is creating positive charge in nitrogen, will be transferred onto your oxygen, creating this thing. Further what will happen? So since we have base also present in the solution, so NH2NH2 and KOH is used. So that reaction medium is basic. Okay, so the reaction is like this, that if you see the reaction equation, you will see that above the arrow we have NH2NH2, that is hydrazine, and below we have KOH, that is acting as a base. Now that base will take one H plus from here. It will take plus H plus one here, and this will kick out. So after this negative charge is developed, it's transferred between carbon and nitrogen, creating an imine, and at the same time this OH is been kicked out, OH minus. Clear? Now this is hydrazone. In the next steps, we will do the hydrolysis of the hydrazone in the presence of a base. How it will happen? Now for that, you can see that this hydrogen is not bonded to a greater electronegative nitrogen atom. So this nitrogen atom is much more electronegative than this one. So it will not donate its electron easily. Therefore, OH minus will take your hydrogen from this nitrogen. This will create a negative charge on nitrogen. You can see here, we have created a negative charge on nitrogen. Now further, what will happen? This negative charge will just propagate throughout this, and the carbon that is having a double bond will take a hydrogen from the solution, creating a diimide. So this is a diimide. It looks like this. Basically, if you draw it, the basic structure of diimide is this. Here R is this group, that is R1, R2 and H. Your imide. Clear? Now what will happen? Again, we have a hydrogen here and we have a base. This OH minus will again take one hydrogen from here, and further this negative charge will again propagate and will take your H plus from water, and N2 will be released in this process. So this whole mechanism, you can say not this whole mechanism, but the hydrolysis of this hydrazone to this normal alkane is being driven by this release of nitrogen gas here. So in each of these reaction, you can see that first of all there is a nucleophilic attack on the center by the hydrazone, and further the base is just deprotonating and removing the group one by one. First your OH minus is released, then further the N2 is released, and after that, and in each of these we are protonating also, because after the release of the say group, you are getting a negative charge on the carbon center that is being protonated simultaneously. After removal of two groups, first of all the OH minus and then your N2, you get your final alkane. So this is the Wolff-Kishner reduction. Next we have aldol reaction. So this is the most popular reaction that you heard. The name, you can say this is the most popular name reaction that you must have heard in the class 12 organic chemistry. So what happens in this reaction? Basically, what do we do? So we take a aldehyde or a ketone. First of all, we take a aldehyde or a ketone. Then we can do it either in the presence of base or in the presence of acid. We are considering here base. So we take a dilute base like our dilute NaOH. Further, the requirement of the reaction is that the carbonyl must have a alpha hydrogen. So what is alpha hydrogen here? So alpha hydrogen is the hydrogen that is present on alpha carbon. And how you would recognize that which one is alpha carbon? So for that, first of all, locate the carbon that is doubly bonded to your oxygen. So this one is the carbon. So this carbon is doubly bonded to your oxygen. Now the adjacent carbon. So now since it has already made two bonds, so two carbons can be at most attached to this carbon. Therefore, there are two alpha carbon that are present, this one and this one. And now you can see that this carbon has hydrogen. So this hydrogen will be your alpha hydrogen. Also, this one is also a alpha hydrogen. These three are also alpha hydrogen. Clear? Now let us see the definition again. So when you treat your carbonyl, that is aldehyde or ketone having alpha hydrogen with dilute NaOH, then it results in the formation of your beta hydroxy ketone. You can also do this reaction in the presence of acid. We'll see both of these. We'll see mechanism of both of these. Clear? Now this reaction is called aldol reaction. So students, one confusion often arises that what is the difference between aldol reaction and aldol condensation? So I've clearly mentioned both of this. So in aldol reaction, there is a formation of beta hydroxy ketone. That is a carbon atom that is attached to a carbonyl center, and beta to that position. So this is alpha, this is beta. There is a OH group attached to this beta carbon. This is called beta hydroxy. Hydroxy means this OH group is present at beta position. So beta hydroxy ketone. Now further, if this beta hydroxy ketone is reduced, or not, I would not say reduced, it is oxidized or dehydrated in the presence of heat due to the removal of your OH group, then it results in the formation of alpha beta unsaturated ketone. So again, let us first name the alpha beta position. This is alpha position, this is beta position, this is alpha. So alpha beta unsaturated means the bond between alpha and beta is double or triple. So here we can see that this is alpha beta unsaturated ketone. Clear? Or aldehyde, that would be according to your substrate. Suppose your substrate is not having this CH3, instead it is having H, then it would be alpha beta unsaturated aldehyde. Clear? Now this is the overall reaction. So two things are to be kept in mind here. First of all, that the carbonyl center of which you are doing this aldol reaction must contain an alpha hydrogen. First requirement. And second requirement, I would say that this should not be concentrated. This base should not be concentrated, or that would result in another reaction. And one more takeaway message should be from this aldol reaction. The simple definition of aldol reaction is that there is a difference between aldol reaction and aldol condensation. So in aldol condensation, we basically reduce the aldol reaction product to an alpha beta unsaturated ketone due to heat. Now how this reaction is going, what is the mechanism, what is the mechanism of this aldol condensation, how is this water removed, we'll see it in the next slide. And we will consider both the aspect, that is your acid catalyzed reaction and your base catalyzed reaction. So first of all, what will happen? So this is our mechanism. Okay, this is our mechanism. First of all, what will happen? First will be activation of the carbonyl center. Now how it is done? With the help of protonation of this oxygen. So what happens here is that the lone pair of your oxygen, this oxygen has lone pair. So this lone pair of oxygen attracts H plus and is being protonated. Now due to this protonated oxygen, its nucleophilicity has increased. We have seen it multiple times that after the chelation or your protonation of this oxygen group, this nucleophilicity of the center increases. Okay. Now what is the next step? Next step is the enolization. Now what is this enolization? So enol is just a tautomer of this carbonyl group. How it is formed? So basically we have seen that, okay, we have formed a double bond between carbon and oxygen and hydrogen. Now this creates a positive charge on oxygen. Now how is this enol formed? Basically what happens here is that, so this is your enol. If you see here, this is your enol. So this H plus that is present here is being so here we have H plus. Okay. So after the protonation, this bond breaks. So let me draw it for you. So here is your, say, carbonyl. This is your carbonyl. Now I have said that it should have a alpha hydrogen. This is the reason behind it. You will see the reason. So first it is protonated. Now this bond has to be broken for the cause of formation of your enol. This positive charge is being neutralized and we get this OH and a double bond O. Now why I am calling it tautomer? Why there are isomers? First of all, because you see that the number of atoms have not been changed in either way. Only the transfer of hydrogen has taken place, although it is done externally, but it still is a transfer of hydrogen that is taking place here. So one hydrogen is being removed and one hydrogen is placed on oxygen. So these both are having the same chemical formula, only the bond formation has been changed, or you can say modified. So this is our enol. This is our enol here. Now in next step, this enol is attacking this carbonyl center. So oxygen has lone pair. So this lone pair will move here and the pi bond will attack on another protonated carbonyl. So what I am saying here is that, see, when protonation occurs, it is not that only one molecule is being protonated. Many other molecules can be protonated. So suppose one protonated molecule is converted into enol and another protonated molecule is being remained in this state. So there can be multiple states, and each of those will have some population in the reaction mixture. So therefore, now this lone pair will be moved here, and this pi bond will attack this nucleophilic center. So that would result in this kind of thing, because after the you can say migration of this bond, or you can say lone pair through this bond, it has created a positive charge on oxygen. Clear? Now, since this is a acid catalyzed reaction, so catalyzed means acid will be removed after the reaction. So this H plus is further removed in the last step. In last, what will happen? Since this is aldol condensation, we can what we'll do? We'll do even Cv elimination. So if you have attended the previous classes, then in that classes you must have heard this thing, that is even Cv. That is basically an elimination reaction, but is occurring in a different way. So what happens in this reaction? So if we have base, then that is even Cv. So since it is not base, it will not do the even Cv, it will simply do the elimination reaction. Okay, sorry for that. So here, first of all, we have a hydroxy group here that will be protonated with the help of acid, that is H plus. Now we have another H2O molecule. It will take one H from here, and this thing will move here, this bond will move here, that is between carbon and hydrogen, and this OH2 plus will be kicked out, resulting in the formation of alpha beta unsaturated aldehyde. So this is the acid catalyzed aldol reaction. Why is it dehydration? Because we are removing H2O in some sense. So OH from here and H from here. So this is your dehydration. Now next, let us see what is base catalyzed aldol reaction and how does it occur. So in base catalyzed aldol reaction, first of all, the deprotonation of your carbonyl group takes place. Here also the alpha hydrogen is important, because this alpha hydrogen is being removed, that is being deprotonated. So there is a base. Suppose we have CH3O minus and Na plus. This CH3O minus will take your H from here, and this bond will travel here. Further, the double bond between carbon and oxygen will be transferred onto your oxygen. This thing is called enolate. There is no much difference between enol and enolate. So it is similar. Suppose when you say carboxylic acid, or not, let us not take carboxylic acid, yes, phenol. So when we take phenol, where H is present in oxygen, we call it phenol. And when this H is removed, it is called phenoxide ion. Okay. Similarly, when you will see the carboxylic acid, and when the H plus of the carboxylic acid is been removed, its name changes from carboxylic to carboxylate. Yes, so similarly, the enol has H here. So if this H is removed, this name changes from enol to enolate. Okay, simple to understand? Yes. Now, since it is a negative charge, this negative charge will propagate back, and the double bond that is being formed initially will be the responsible for the attack on the carbonyl center. Okay, so this is formed, and the double bond between carbon and oxygen is being transferred onto oxygen, creating negative charge on this thing. Now in the start of the reaction, this CH3O minus has taken one H plus from here, and since it is a base catalyzed reaction, this CH3O minus concentration should not change, so it should be given back. So the CH3OH is being taken up, this H of CH3OH has been taken up by the O minus of this alpha beta hydroxy ketone, this beta hydroxy ketone. So this O minus take this H, and we form at last your aldol product. Okay, now we will see the dehydration. So same thing written here. So first your enol formation will take place, then the nucleophilic addition is taking place in this reaction. So it is why it is addition, because we are not removing anything, we are just adding this group. If something was removed, or say if some living group was there, then this would have left the center, and we would only got your nucleophilic substitution, but it is nucleophilic addition reaction. At last, as I have told, you will see the dehydration. So this is your, say, this is your even Cv reaction. Why it is called even Cv reaction? Why this elimination is different? Because in this elimination, the conjugate base that is present here, it helps in the removal of the OH group, because now we are not having H plus in the solution. So this will not be protonated, and OH minus is not a good leaving group. So what happens here? This CH3O minus take your H plus from here. This creates a negative charge here. Now this negative charge propagates onto this oxygen and it reverts back and kicks out this OH back. So if you have a base that is present, if you have a say negative charge stabilizing factor that is present on alpha position to the group that is being eliminated, then in that case your bad leaving group can also be removed. So basically, what is the structure required for even CV elimination? So at beta position to this bad leaving group, we have a negative charge stabilizing factor. So the OH minus comes and take this H from here. Now this bond will propagate and move off to oxygen. And here will be a double bond and OH. Now further, this negative charge that is present here, it will be propagated back and the double bond will move here and OH will be kicked out. This will further create your required product, that is alpha beta unsaturated ketone or aldehyde if this R is equals to H. Okay, clear? So this is your overall reaction. First, deprotonation. So if you contrast it to the acid catalyzed, so it was protonation rather than deprotonation. Then it was enol formation. In case of acid, it is enolate formation here. Next thing is same, that is the nucleophilic addition. Both of these are undergoing the same thing, and the dehydration is also taking place. The difference between both of this dehydration is that in the acid catalyzed dehydration, we first convert the OH into a good leaving group, that is H2O, by protonation of that OH group, and then we just kick it out. But in the case of your base, what do? We do it with the help of your even CB elimination, that is conjugated base elimination. So this was the mechanism for both acid and base catalyzed aldol reaction. Clear? Now, next, let us move to some illustrations here. So now this aldol reaction can be of multiple types. So here I have put some. So if we have two ketones, that it is self aldol of ketone, or here is the acetone specifically, or we have aldehyde, then it will be self aldol of aldehyde. Here it is acetaldehyde. Then one more case can arise, that is of crossed aldol reaction. Crossed aldol reaction. And then we have your intramolecular. If aldol reaction takes place within the molecule, then it is called intramolecular aldol reaction. So the first two should be clear. There should be no confusion about this self aldol. Either of these can be protonated, or you can say deprotonated based on the circumstances, whether it is acid catalyzed or base catalyzed, and another molecule will be undergoing your nucleophilic addition. Clear? All of these are alpha beta unsaturated product, means you are doing aldol condensation. Now, what is crossed aldol here? So in crossed aldol, we take two different type of ketone or aldehyde, or you can say either ketone or aldehyde couple. Here we have taken one ketone and we have taken one aldehyde. Now who will decide that which of this will be deprotonated? So this reaction is not difficult to understand. Why? Because there is no alpha hydrogen present on this aldehyde. So it is a simple attack. So first of all, suppose I am taking the base catalyzed mechanism. So first of all, this H will be deprotonated. This will move here, move on to this oxygen. This oxygen lone pair will be again pushed back, and the carbonyl center of this benzaldehyde will be attacked. And further, upon dehydration, you will get your required product, that is alpha beta unsaturated carbonyl group. Now what happens if that it has also one H present here? What I'm saying, suppose we take an example like this. Now which one will be deprotonated and which one will be nucleophily attacked? So in this case, we see the group that is less hindered, or you can say that is more vulnerable to this nucleophilic addition attack will not be deprotonated. Okay, so out of these two, this one is more vulnerable to your nucleophilic attack. So this one will be deprotonated. Okay, and further this attack will take place, and your required product you can just try to solve it. So what we have taken cyclohexanone and acetaldehyde. Now try to do it both with the help of acid and base catalyzed reaction, or you can say acid or base catalyzed mechanism. Clear? Next is an interesting question, you can say an interesting illustration in which we have done self-aldol reaction, or you can say intramolecular, so not self-aldol, intramolecular aldol reaction. Self-aldol is this one. In this case, we have a single molecule that has both the substrate required for your aldol reaction. Now you have to decide that which one will be deprotonated and which one will attack. Now it is very clear here that if this one would have been, say, deprotonated, then there would be large steric hindrance for the attack on this carbonyl center. Therefore, what happens is that this one is deprotonated. Now you would say, sir, there is also a possibility of deprotonation of this one. Now, if you try to move in this fashion after deprotonating this one, then you will get a very strained bridge. Okay, just try to do with yourself. I will give the correct answer in next class, but try to do this thing. Okay, now the attack will take place from here. If we do it from here, then so let me do it now only. Okay, just take a different page. So what I'm saying is that we are taking one thing. Suppose we deprotonated this center. Now how will this attack take place? It will do attack here. And how many length chain will be formed, or you can say member ring will be formed? 1, 2, 3, 4, 5, 6, 7 and 8 member ring. So 4 is from here. 1, 2, 3, 4. Now 5, 6, 7, 8. 4 carbons are to be drawn. 1, 2, 3, 4. So it would result in this kind of product. Clear? Now you can see that this is a kind of strained ring now, because this has been frozen in some way. Okay, and this creates a lot of strain in this angle here. So due to this reason, we are not doing this kind of attack from here, rather than we are attacking from this side. And also the 6-member ring is much more favored than this large 8-member ring. So this can be also a great factor, that the 8-member ring is say less favorable as compared to your cyclohexane stabilized ring. One more question can arise, that why do not we do the deprotonation from here, and why not from here? Okay, so the question can be this also: why do we form this kind of bond only from this hydrogen only? So the answer is very clear. First of all, the even CB will not be favored from this direction, because the base will be far away from here, and also the product from here is a alpha beta unsaturated system, that is a conjugated system. So this conjugated system is kind of stabilized. Okay, so for that reason we do take the proton from this center. Okay, so this was about the aldol reaction. Both we have covered acid-base catalyzed reaction. In addition to that, we have seen some illustration. Now, what happens if we take concentrated base in place of a dilute base, and the next thing we will do is we will take aldehyde or a ketone that is incapable of having your alpha hydrogen. So what will happen in that case? So in that case, in which we have the aldehyde does not have any alpha hydrogen atom. So in that case, your aldehyde undergoes self-oxidation and reduction, that is the disproportionation reaction. So this is very important, that if something is getting oxidized and reduced simultaneously, if the same molecule is getting oxidized and reduced, then the reaction is called as disproportionation reaction. So we do it in the presence of an alkali metal. So in this reaction, one molecule of aldehyde is reduced to alcohol, and while another is reduced to carboxylic acid. So what do you mean by this? That we are again taking 2 moles of the same compound, or 2 molecules of the same compound, similar to that of our aldol reaction, but the formed product is alcohol and a formate, or you can say carboxylate. Okay, clear? And one more change in condition is that conch and the removal of your alpha hydrogen, or the absence of your alpha hydrogen. Now, how does this reaction goes? We will see it in the next slide. So the conditions are no alpha hydrogen should be present. So it is a disproportionation reaction. The most important point, why it is disproportionation? So this molecule is being oxidized here, so reduced here, as we are adding hydrogen, and it is being oxidized also because we are adding oxygen. So since the same molecule is undergoing, so you would say that, okay sir, this molecule is undergoing this reaction, this molecule is going this reaction. So how is it the same molecule? I would not the same molecule, I would say the same compound is going the reduction and oxidation. Clear? Okay. So it is getting oxidized because it is adding one oxygen, and it is getting reduced because one hydrogen has been added here. So it is a disproportionation reaction. And why it is a disproportionation? The reason is self-oxidation and self-reduction. Next, let us see the mechanism of this reaction. How does this mechanism goes? So, as I have told you earlier, that it would not contain any alpha hydrogen. It will not contain any alpha hydrogen. So, what will happen? This OH minus will attack this center and create this kind of intermediate. How it is attacking? OH minus is a nucleophile, nucleus loving. So its electron will be donated onto this carbon. Now the pi bond between carbon and oxygen is being propagated onto the oxygen, creating a negative charge on oxygen. Clear? Now again we have OH minus, that will take one H plus from here and will create a dianion. Now as we have a dianion, this negative charge, this comes back, that is very unstable, this space is very unstable, this negative charge will come back and will kick out this H from here, and this H will be having a negative charge along with it, that is hydride. Now this hydride will be donated onto this center and it is reduced to this alkoxide because we are adding one hydrogen. On the other page we are seeing that we are converting your dianion to your carboxylate, because now the carbon has a double bond with your oxygen rather than a negative charge on both oxygens. So this is your carboxylate plus one alkoxide. So why I'm saying alkoxide? So this is basically a derivative of your alcohol in which we have removed one hydrogen. At last we have water in the solution that will protonate both of this group, that is your carboxylate and your alkoxide. So that would result in your alcohol and carboxylic acid. So this reaction mechanism is quite peculiar to look. Why is it so? Because we have not seen earlier the departure of any hydride group. In normal organic synthesis, you must have seen the hydride group donation in case of the reduction that is done by lithium aluminum hydride or any hydride donor. But it is an organic compound and this thing is rare. So for this condition to happen, or for this reaction to happen, we apply extra heat, and also we take your conch base, that is conch KOH or conch NOH. So if we take conch dilute NOH, this reaction will not proceed further. So today what we have seen are the reactions that are basically related to the alpha hydrogen of this say aldehyde or ketone, in which we have seen two types of reaction. First one is the aldol reaction, which can be done both by say your base catalysis and your acid catalysis, and there should be availability of alpha hydrogen for that. For the one more point to remember is that in case of say aldol condensation, we have a alpha beta unsaturated bond, that is present alpha beta in with respect to your carbonyl center. Why in your aldol reaction we just have a beta hydroxy ketone. We have a OH group that is present beta in beta position in with relevance to your carbonyl group. Further, we have seen three types of your aldol reaction: self, crossed, and intramolecular. In self aldol condensation, we do not have any problem. We have seen some mechanism, but in crossed aldol condensation or in aldol reaction, you must deprotonate that substrate. So we take two types of substrate, two types of aldehyde and ketone. Suppose both of them have alpha hydrogen, then which one will be deprotonated is based on factor that is that molecule more say vulnerable to your nucleophilic attack or the other one. The one which is less say vulnerable to your attack, it's deprotonated, and that other one, the former one, which is good to your nucleophilic addition, is being attacked by the enol or enolate that has been formed. And in intramolecular hydrogen say aldol reaction, both the substrate and your reagent are both the substrate, that is your both the carbonyl group are present in the same group. And I would suggest you that you should be very keen about this self aldol reaction, as it is a very good reaction. Okay, it can be asked directly in the exam, so you must try to figure it out as soon as you see two carbonyl groups, whether on one functional group, one compound or another compound, and plus you have a dilute NaOH. Remember it, dilute NaOH or dilute KOH, then there's a high chance that it would give you your aldol reaction, that is the self aldol reaction. Now what happens to the compound that are not having alpha hydrogen? For that we take another reaction conditions. The first change in reaction condition is that we supply extra heat in the first step as only, plus we take concentrated acid base in place of your say dilute NaOH. Okay, so for that, this is the mechanism, and it is a disproportion reaction because your aldehyde or ketone will be subsequently reduced to alcohol as well as to your carboxylate ion. And now you know that alcohol is a reduced form because one hydrogen is being added to your carbonyl group or the carbonyl oxygen, whereas the carboxylate is an oxidized form because one oxygen is been added to your aldehyde or ketone that was undergoing Cannizzaro reaction. Now, since both oxidation reduction are occurring for the same compound, that reaction will be called as disproportion reaction. Now, if you look at the mechanism here, the mechanism is basically a sum up of three things. First of all, the nucleophilic attack by the OH minus, further the attack of the hydride on the another atom, that is basically due to the formation of dianion. Okay, so it would result in carboxylate and your alkoxide. Okay, clear? Now next what will happen? The two anion will be protonated in the help of your water. So this was for today's class. So what do we do in the next class? In the next class, we will start the new species, that is carboxylic acid. In that lecture series, we will see basically the nomenclature of the carboxylic acid and the methods of preparation. Okay, so I would suggest you that you should be well aware about the acid derivatives of your carboxylic acid, like or acyl chloride or acid anhydride, or you say amide. So those species should be well identified. So I'm just giving a glimpse of it. Suppose we have a Cl here, so we call it as acyl chloride, no problem. Now next, suppose we have NH2, we call it as amide. Now next, suppose we have your another group like this that is present. So what you will call it in that case? You will call it an anhydride. Now if this group is not O and it is simply a R, that is suppose CH3 group, then it will be ester. Okay, no problem. So you must be well aware about the structure of all this derivatives of your carboxylic acid, in which you have removed your OH group with different substrates. Okay, no problem. So you should remember this. So in the next class, first we will see some common nomenclature, We will see some common nomenclature of some commercially available carboxylic acid. Okay, and plus we will see the methods of preparation along with the mechanism. So I am covering the mechanistic part also because that would be appropriate and would help you to appreciate the reaction product. So with this, I would end my lecture. Thank you.